Students, today we are going to discuss the filling of orbitals in an atom. Filling of orbitals in an atom. You see that the filling of electrons in different orbitals of an atom is governed by three different rules. And these are Pauli's exclusion principle, Aubert principle, and Hans rule of maximum multiplicity. So these are the three principles: Pauli's exclusion principle, Aubert principle, and Hans rule of maximum multiplicity. These three rules govern the filling up of electrons in different orbitals of an atom. So students, now we'll see Pauli's exclusion principle. This rule states that no two electrons in an atom, no two electrons in an atom can have the same set of four quantum numbers. Means, if we have n is equal to 1, then for this we will have L is equal to 0, M is equal to 0, L is less than or is equal to n minus 1, greater than equal to 0, so L value will be 0 as n is equal to 1, and M is less than or is equal to plus L, greater than or equal to minus L. So just we think that, consider this as orbital. So the same set of four quantum numbers, here we see the same set of four quantum numbers, means four quantum numbers cannot be equal for the two electrons present in an orbital. So up to 3 they may equal. They may be equal for up to 3 quantum numbers. They may equal, but the fourth one is not equal. So if we have one orbital for n is equal to 1, if we have this orbital, we have two spins, or two spin values possible. One is plus half, another is minus half. So if for one electron plus half, another for another electron minus half, if we put one here for another, that will be minus half. Now you see, if we put another electron in this orbital, another electron if we put like this, then the spin for this will be plus half, so this plus half, and the spin for this is plus half. So what happens? Four quantum numbers will be same for these electrons. If we put another electron in this, then what will happen? The four quantum numbers will be equal. So we see for this electron the address will be n is equal to 1, L is equal to 0, M is equal to 0, S is equal to plus half. For this electron, N is equal to 1, L is equal to 0, M is equal to 0, S is equal to minus half. So the addresses are different for these two electrons. Means up to 3 quantum numbers they may be equal, but the 4th quantum number for the electron which is present in the same orbital cannot be equal for the 2 electrons which are present in the same orbital. So now another statement of Pauli's exclusion principle comes, and which is an orbital can accommodate a maximum of 2 electrons with opposite spin. This means that only 2 electrons may exist in an orbital. Only 2 electrons may exist in an orbital which are having opposite spin. If one spin is plus half, the other one spin must be equal to minus half for the 2 electrons present in the same orbital. Students, based upon this Pauli's exclusion principle, we may find out the maximum number of electrons present in a shell. We know that number of orbitals present in a shell is equal to n square. So total number of electrons, therefore total number of electrons present in a shell is equal to twice n square. Means total number means maximum number of electrons present in a shell will be twice n square, as there are n square orbitals present in a shell, and if one orbital can accommodate a maximum of 2 electrons, if one orbital can accommodate a maximum of 2 electrons, then for n square number of orbitals we are getting 2 into n square. 2 into n square means twice n square number of electrons in a shell. Just if we consider n is equal to 3 means third shell, then what will happen? Their number of electrons will be 2 into 3 square is equal to 2 into 9 is equal to 18. For n is equal to 2, 2 into 2 square is equal to 2 into 4. That means 8 number of electrons will be present in the second shell. 18 number of electrons, maximum electrons, 18 number will be for the third shell. For n is equal to 1, 2 into 1 square is equal to 2 into 1 is equal to 2. So maximum 2 electrons can be present for the first shell. Students, also we may calculate the maximum number of electrons present in a subshell. That is, if we have a subshell, then how many number of orbitals are possible for this S subshell? L is equal to 0, means M is equal to 0 for this. So only one orbital only one orbital. So maximum 2 electrons can be accommodated in the S subshell. For P subshell, we have L is equal to 1, means M value for this will be -1, 0, plus 1. This we know that L is equal to 1, for that M will be less than or is equal to plus L and greater than or is equal to minus L. So L is equal to plus 1 means L is equal to 1 means minus L will be -1, plus L will be plus 1. So from -1 to plus 1, from -1 to plus 1, in between these two 0 is available. So we have 3 orbitals. We have 3 orbitals, 1, 2, 3. So maximum 6 electrons are possible. And if one orbital, 2, another 2, another 2, so maximum 6 electrons can be possible for P subshell. For D subshell, we have L is equal to 2. So M is equal to -2, -1, 0, plus 1, plus 2. Means 1, 2, 3, 4, 5. 5 orbitals are possible for D subshell. So if one orbital can accommodate 2, 2, 2, 2, so there will be 2 into 5 is equal to 10 electrons. So maximum number of electrons that can be accommodated in this subshell will be 10. Similarly for F subshell, we know for F subshell L is equal to 3. M will be -3, -2, -1, 0, plus 1, plus 2, plus 3. So there are 7 orbitals. So if 7 orbitals are there, 2 into 7, that means 14 number of electrons are present, or maximum 14 number of electrons may be present in F subshell. Friends, we also know that total number of orbitals in a subshell is equal to twice L plus 1. So if one orbital can accommodate maximum 2 electrons, then twice L plus 1 number of orbitals will be able to accommodate 2 into twice L plus 1 number of electrons. Means we know total number of orbitals present in a subshell is twice L plus 1. So if total number of orbitals is twice L plus 1, and if one orbital can accommodate a maximum of 2 electrons, then what will happen? There will be 2 into twice L plus 1. 2 into twice L plus 1 means this number of electrons may be accommodated in a subshell. We may solve one question. Find the number of electrons for which n is equal to 2, m is equal to 0, s is equal to -half. So we have n is equal to 2, m is equal to 0, s is equal to -half. So here it is given that for these values, how many electrons, total number of electrons may be possible. So if we have n is equal to 2, we now see if we have n is equal to 2, L will be our 0 and 1, means 0 and 1. L is actually less than or is equal to n minus 1 and greater than or is equal to 0. M is less than or is equal to plus L, greater than or is equal to minus L. So m value will be for this 0. If l value is 0, m will be 0. If l is 1, for this m will be minus 1, 0, plus 1. Means minus l will be minus l, minus 1 for 1, minus l, minus 1, then plus l will be plus 1, minus 1, plus 1, in between there 0. So here we have 1 orbital, here we are getting 3 orbitals. Now you see m is equal to 0 for this orbital. We can see that m is equal to 0. For this m is equal to minus 1, 0, plus 1. So m is equal to 0 here for 1 orbital, m is equal to 0 here for 1 orbital. Here maximum 2 electrons. So one electron will have plus half spin and the other one will have minus half. Here one electron may have plus half spin and the other one may have minus half. So here one electron we are getting which is having minus half spin. Here one electron we are getting which is having minus half spin. So total number of electrons having n is equal to 2, m is equal to 0, s is equal to minus half will be 2. Here 1 and here 1. So total number of electrons for which n is equal to 2, m is equal to 0, s is equal to minus half will be 2. So students, we may see another question. Calculate the total number of m values for n is equal to 4. We see that n is equal to 4 here. So for n is equal to 4, we are getting l is equal to 0, l is equal to 1, l is equal to 2, l is equal to 3. As l is less than is equal to n minus 1 and greater than is equal to 0. So n minus 1 will be 4 minus 1, 4 minus 1 is equal to 3. So up to 3, from 0 to 3, we will get the values of L. Now for L is equal to 0, M is equal to 0, as M value will be less than is equal to plus L, greater than or is equal to minus L. So M will be here minus 1, 0, plus 1. For L is equal to 2, M will be minus 2, minus 1, 0, plus 1, plus 2. As 2 minus L, for 2, L is equal to 2, minus L will be minus 2, plus L will be plus 2. So from minus 2 to plus 2, in between minus 1, 0 and plus 1 is there. So for L is equal to 3, we have M is equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Means for L is equal to 3, minus L will be minus 3, plus L will be plus 3. So in between these two, minus 3 and plus 3, in between these two, we have minus 2, minus 1, 0, plus 1 and plus 2. So here 1 M value is there, here 3, here 5, means 5, here 7. So total will be 1 plus 3 plus 5 plus 7 is equal to 7 plus 5, 12, plus 3, 15, plus 1, 16. So there are 16 M values for n is equal to 4. Let's see another question. Using S, P, D and F notations, describe the orbitals with the following quantum numbers. Number 1, n is equal to 1, L is equal to 0. Number 2, n is equal to 2, L is equal to 1. Number 3, n is equal to 3, L is equal to 2. Number 4, n is equal to 4, L is equal to 1. So we have in number 1 n is equal to 1, L is equal to 0. So L is equal to 0 means S subshell. So we are getting 1 s orbital. 1, number 1, principal quantum number is 1. So 1 is first and then the subshell, S subshell. Number 2, n is equal to 2, L is equal to 1. L is equal to 1 is our P subshell. So it will be 2P. Number 3, n is equal to 3, L is equal to 2. L is equal to 2 means our D subshell. So the orbital will be 3D. And number 4, n is equal to 4, L is equal to 1 is our P subshell. So the orbital is our 4P. 4P orbital. So n is equal to 1, n is equal to 1, L is equal to 0, L is equal to 0 means S subshell. So 1s is the orbital in this case. In this case, n is equal to 2, L is equal to 1, L is equal to 1 is our P subshell, it is our P subshell, so the orbital is 2P. In this case, n is equal to 3, L is equal to 2, so n is equal to 3, L is equal to 2, 2 is D subshell, so our 3D subshell is this, and n is equal to 4, L is equal to 1, L is equal to 1 means our P subshell, so here it will be 4P orbital. Another question. We see an electron is present in one of the 3D orbitals. Find the possible values of n, L and m for this electron. We see 3D orbital. In case of 3D orbital, here n is equal to 3, L is equal to 2. Means n is equal to 3 here, L is 2. For D subshell, L is equal to 2. So ml will be m is equal to -2, -1, 0, +1 and +2, as m is our less than is equal to plus L and greater than is equal to minus L. So here is this. The possible values for n is 3, L is equal to 2, and m will be -2, -1, 0, +1 and +2, as 2, L is equal to 2, so minus L, L is equal to 2, so minus L will be -2 and plus L will be +2. So in between -2 and +2 there will be -1, 0 and +1. So the possible values of n will be 3, n will be 2 and m will be -2, -1, 0, +1 and +2.